tech. And her shift in academic focus from a master's thesis in experimental electric propulsion to her current work that we're going to hear about today in modeling ocean dynamics on icy moons was inspired by a planetary physics class she took as an elective at Georgia Tech. So that's kind of neat. Sara's graduate work has been very well funded, including multiple competitive awards. So an NSF GRFP, a NASA Finest Award. So very successful in funding her research. And she's also been a recipient of a Student Research Award in Planetary Habitability from CPSH, where she was collaborating with a number of our members, I think, on the work we're going to be hearing about today. And so with that, I'll let Sara take it away.
Great, thank you for the introduction. Yeah, this has been a really fun project to work on, so I'm excited to kind of share some of the things that I've been doing on this. Okay, so yeah, kind of as we were talking about just before this began, Europa is a really interesting place. It's very much a usual suspect in the search for life in the solar system, but particularly interesting among ocean worlds because of its relatively young surface and very interesting geomorphology. So here I'm showing kind of a collage that NASA put together that highlights some of the really diverse and interesting types of terrains on Europa's surface. Yeah, and until, you know, Europa Clipper or another mission to the Jovian system can give us more data to work with, the data that we do have at Europa is fairly scarce, at least when you're considering ocean dynamics and comparing it to kind of the types of data that we have for Earth's ocean. However, we do have some really nice images of the moon's surface, and that strongly points at recent or ongoing resurfacing processes and exchanges between this outer icy shell that we can observe and a liquid ocean underneath, which is what I'm most interested in. So on Earth, we know that the global ocean circulation is really critically important in the transport of heat and salt and nutrients that sustain the ocean's biosphere. So when we're thinking about habitability of other moons and other places across the solar system, I think ocean dynamics is a really big piece of that puzzle. So I mentioned that kind of, you know, direct observational data of Europa's ocean is so far scarce, but what we do have is a really interesting analog here on Earth. So we have ice-covered portions of Earth oceans, and we have data from Antarctic field studies. And from this data, we know that certain regions, including the boundary layer that directly separates the liquid water ocean from the ice layer, is really critically important. That small millimeter thin region, it's called the interfacial sublayer in a lot of the literature, that separates the water from the ice, has a disproportionately large impact on the movement of global water masses and determining the ocean's overall energy budget. So this region, the boundary layer that separates the ice and the ocean, is an area that I've focused a lot on my work on this problem this past year. So I'm not the first person to attempt to study Europa ocean dynamics, not at all, with a 3D circulation model. But one of the issues is that the results and the conclusions from existing models of Europa's ocean are significantly divergent, and their conclusions lack agreement. So I think this essentially boils down to differences in the types of boundary conditions that are set on these models and the simplifying assumptions that really need to be made in order to model global ocean dynamics in this setting. And so I'm hoping to kind of bridge the gap between what we know for Earth's ocean and Antarctic field studies and the data that we have from under Antarctic ice shelves and what we're able to model in an icy ocean world. So the plan is to use MITgcm, so a terrestrial ocean model that's very powerful compared to a lot of the models that are applied to Europa currently, and try to adapt it and come up with new boundary conditions and some new driving forcing equations, and particularly a sophisticated ice shell model that can really kind of model this environment well. So when we think like high level about the processes that play in planetary ocean circulation at Europa, from a more of a system science standpoint, we can identify mechanisms that are the same or similar to those that operate on Earth's ocean, But there are also some that apply to Earth and not to Europa, such as surface wind stresses or insulation of the upper ocean layer, and also those that may be relevant to Europa that are not to Earth. I think one of the more interesting ones is the way that gravity and rotation interact in this system because of the much larger oceanic depth scale at Europa. So compared to its planetary radius, Europa's ocean is a lot deeper. And as a result, the Coriolis effect is really non-negligible in the horizontal direction, whereas that's, the thin shell approximation more or less applies to Earth in a lot of global ocean models. So that is definitely not the case at Europa, and something that kind of needs to be addressed in the model forcing equations for this general circulation model. But yeah, thinking about kind of all of these mechanisms, bottom heating from the mantle, salinity fluxes from the freezing and melting that may be happening at the ice shell, the heat flux that's happening at that very interesting boundary layer region, and then very interesting tidal heating dynamic. There's kind of lots of things to try and capture in this model, and one of the big motivators is to try and understand the relative weight and importance and how these interact together. So I mentioned at the beginning that I think one of the big pieces of this puzzle is this ice-ocean boundary layer. And there's a really widely adopted method for parameterizing this process in terrestrial ocean models. And this is the 3-equation parameterization, which is not a very creative name, but it is descriptive of what's happening here. So there's 3 equations that describe the fluxes of temperature and salinity that kind of traverse from the ice shell to the boundary layer, and then from the boundary layer to and from the liquid ocean, or mixed layer as it's called here. So that's the subscript M. And the 3 unknowns here are the mass flux across the boundary layer, the M dot, which is an indication of whether you're currently in freezing or melting regime. So in this case, negative is melting and positive is freezing for M dot. The temperature of the boundary layer, and then the salinity of the boundary layer. So 3 equations, 3 unknowns you can solve for that M dot. A couple things to point out here is that the salinity of the ice shelf, S subscript I in this case, is generally neglected in terrestrial ocean models. And that's a pretty good assumption for most of the ice that we see on Earth. But there is a lot of interesting research out there on how impurities frozen into the ice can affect these processes. So Jacob Buffo, from former Brittany Schmidt student, and others are doing kind of some really interesting research. Krista's done work with her students on this as well, looking into this. And then another thing that kind of is important to point out here is that this parameterization in its full form does use experimentally derived turbulent transfer coefficients that's from Antarctic data. So obviously we don't have these same measurements for Europa yet, but I think there's still value in kind of using the Earth constants as a starting point. And this is kind of one of those areas where I think we can pull from terrestrial literature to kind of try and build a more realistic model of what's happening at Europa. And then finally, the last thing I want to mention on this kind of physics is that an underlying assumption in this formulation is that you need to linearize the equation of state for seawater in order to kind of close the solution. And that really implies that the temperature of the boundary layer is a linear function of salinity. It's in fact weakly nonlinear on Earth. And we know that on Earth, salt diffuses at least an order of magnitude slower than heat, so it's a pretty good assumption. But on Europa, different ocean chemistry that could behave very differently. So yeah, there's a lot of ways that this could be different, but I think still a very useful formulation to kind of try to apply to Europa. So my research my goal for my graduate work and goal for this project is really to develop a tool, and that's this Europa GCM that can capture global heat, salt, and momentum fluxes, and that really has a more realistic ice shell model that can account for this freezing and melting physics. And I think one of the big challenges of this model is to capture a resolution in the model, the spatial resolution and a temporal resolution that's able to capture the kind of individual flow features. So like plumes that could exist, convective plumes, as well as their impact on like global ocean behavior, like overturning. So I'm still working on building this code, so I'll show you kind of some bits and pieces that I've gotten some preliminary results for, but the idea is that once this exists, I can use it to perform some sensitivity studies and kind of understand what, you know, Europa's ocean would behave differently if there were, you know, small or large scale topographies under the ice shell, different ocean chemistries, different initial and boundary conditions. So yeah, kind of to explore a range of possibilities throughout my graduate work. So kind of to make it clear how this tool and the activities I've just outlined will contribute to the literature, I've come up with a few kind of driving science questions that motivate this work. So the first one, question one, is really to explore the parameter spaces for turbulent diffusivities and viscosities and work towards like narrowing the gap between the model's horizontal grid scale and the length scale of convective columns that are expected at Europa. So this will involve kind of some theoretical work that I've started, but have not really kind of finished on rotating convection theory and understanding kind of the best that this model needs to be in order to really capture what's going on from a resolution standpoint. The second question is about looking at how eddy diffusivity modulates heat flux in turbulent flows and how it influences mixing, melting, freezing at the boundary layer. So despite its really important role in the heat balance, eddy diffusivity is for the large part very poorly constrained and often exploited as a tuning parameter in both terrestrial and planetary ocean models. So I think that's something that I really need to put some thought into and understand how I can do that better in this model. And then this third part is to kind of, I mentioned this earlier, it's to really add to the discussion of what circulation mechanisms are dominant in Europa's ocean and whether they're from hydrothermal plumes or quasi-3D turbulence, baroclinic eddies, or buoyancy-driven flows from ice freezing and melting, how those all interact together and which one's dominant in this regime. So a little bit more about MITgcm and kind of to address the question of why I chose to use this tool, I want to kind of briefly discuss its setup and some specific packages that I think are very useful for this problem. So it's a 3D grid that employs a full non-hydrostatic incompressible Navier-Stokes formulation. So essentially what this means is it's capable of resolving really small scale float features, which I think is not something that's always possible in planetary ocean models. And in its most basic setup, it operates essentially with 4 prognostic equations for the velocity and zonal and meridional directions, temperature and salinity, and then 3 diagnostic equations for, well, in the full non-hydrostatic formulation, there's 4 diagnostic equations. But what makes this model, I think, very useful are the specific packages that have been built kind of as options within the code. One of them is a shelf ice package, and that kind of implements a version of the 3-equation parameterization that I discussed earlier. And I think that'll be really useful for a global ice shell code. And then the other is a deep atmosphere package that removes the thin shell approximation that's often used in terrestrial ocean models and reintroduces the metric terms that are important for that horizontal component of the Coriolis force. So to give you some examples of what you can get from this model and kind of in this case, the shelf ice package, I've set up kind of some testbed models to give preliminary results with a few simple kind of verification experiments. So in this situation, we have water that's initially at rest with a uniform potential temperature and salinity. And we're introducing like a very simple model geometry that'll kind of act as ice shelf topography. In this case, just a ramp And we're focusing on this kind of case study of just the ice ocean boundary layer. So it's not a global circulation model in this result, but it's instead just a section of that boundary layer. And then I used friction and mixing parameters that are relevant in Antarctic settings on Earth. So here's that kind of simple model topography, and then kind of a table of the mixing parameters that I used for this model. Kind of to show you some types of results that you can get from this. On the left, we have a barotropic stream function of vertically integrated mass transport, and on the right, it's an overturning stream function of zonally integrated mass transport. So this is kind of fun because you can see the formation of a gyre and a western boundary current type feature forming underneath the ice shelf base, which is similar to what we'd expect for observations of similar conditions on Earth. So it's kind of neat to see that the flow features are really like checking out with the model forcing equations and the physics that went into this. So in the gyre, that circular flow feature, the melting from the increased pressures at depth as you go down the ramp are causing, the melting is causing a buoyant kind of fresh meltwater plume to rise along the ramp, and that causes kind of the circulation and the formation of that flow feature. And I think it's interesting to think about this in the context of both small and large scale topography variations that may exist under the ice at Europa. And what I mean by that is, you know, the roughness under the ice could cause a very different drag coefficient, and kind of small scale turbulence that could affect flow, whereas like a larger ramp or large scale ice topography could really affect pole to equator circulation. And these results kind of, they agree with isopycno models that model things like the western boundary current transport. So that was that one. And so here I'm showing kind of a different result, the melt rate, so that m dot in the 3-equation parameterization. In this case, it's in meters per year, and it's a little bit kind of hard to put labels on all of these contours, but I've kind of highlighted where m dot is negative, in this case melting, and where it's positive, that upper section, or freezing. So you can see regions of both freezing along the western boundary current and then melting closest to the mixed layer. So the refreezing that's happening along the western boundary current is because of this pressure dependent freezing point of seawater that I mentioned is changing as we go down the ramp that I introduced in the model geometry. And we know that it's kind of interesting to think about the implications of these results, because temperature, we know, is proportional to heat flux per grid cell volume. And so larger, thicker grid cells, or a coarser model resolution, is going to be cooled a lot more slowly than a denser grid with thinner cells. So if you have a temperature of the boundary layer that's fixed at the freezing point, that difference across a thicker cell is going to lead to a larger heat flux and larger melt rates than a denser grid. So this does introduce kind of noise into the model, where jumps in layer thicknesses can kind of cause some jumpy data, some noise in the data. And so it does definitely call, I think, in this area where freezing and melting is happening and where phase changes are occurring, for a denser vertical grid structure. So that's something I've been kind of working on more recently, is to work on something I think could help with this issue, which is grid remeshing. So MITgcm was developed with a fixed vertical grid, which can be problematic, as I mentioned, when you want to simulate freezing and melting, or a really dynamic process. And so the modeling challenge is that freezing and melting do not really occur within a model run. So a melt rate m dot is calculated for each grid cell, but only so that the correct amount of heat and salt are added to the adjacent grid cells. You cannot actually like change the identity of the grid cell mid-model run from ice to ocean or vice versa. So I think grid remeshing is a possible solution to this, where you can, in fact, change the identity of the cell by performing computations for fractional grid cells. And so it's just a way of kind of increasing the spatial discretization without really increasing model run times as much as you'd need for just a significantly denser grid throughout the entire model. Okay, so I'll try and move a little bit faster because I'm running a little bit behind. But so kind of towards the goal of selecting an appropriate grid scale for my model, I'd like to follow processes similar to what others like Krista Soderlund has done for icy satellites by rotating or by leveraging some rotating convection theory frameworks and trying to understand the scales of features that could exist at Europa by really understanding which convection regime it fits into. So Europa's convective regime is based on non-dimensional flow parameters like Ekman and Rayleigh number estimates. And per Krista's work on this topic, Europa lies at the unbalanced boundary layer and non-rotating heat transfer boundary. And so the fact that it lies at a boundary does make this a little bit more difficult because this is the point where the influence of rotation is lost locally and you have a breakdown of geostrophy. So this is kind of something that future work for my graduate work in order to develop appropriate boundary conditions and really kind of understand the degree to which I need to use things like active grid cell remeshing and set up appropriate boundary conditions. So we know on Earth, understanding the convective regime is really important, not just for kind of placing bounds on the expected flow features, but also in understanding large-scale ocean dynamics. So oceanic deep convection is a process by which cold water is sinking at high latitudes and upwelling along surfaces of constant density that connect kind of the deep ocean to the sea surface in places like the Southern Ocean around Antarctica. So in MITgcm, where people have used this code to kind of study Southern Ocean and Antarctic freezing and melting, they developed a specialized package, the deep atmosphere package, which is especially relevant to Europa because it increases the oceanic aspect ratio. So to give you an example, on Earth, this is around 10 to the -3. So in that regime, the vertical component of the Coriolis force is dominant, whereas Europa is a much deeper ocean with respect to its planetary radius. So that same ratio, L/H, is about 1/16. So in this case, the horizontal component of the Coriolis force is important here. So this figure is kind of complicated and it's not kind of all relevant to Europa, but it does go to show that there are a lot of processes that are really important in regions where you have active freezing and melting and these rapid changes in density and temperature, which we'd expect at Europa. So to kind of understand how this package can be used and how it can be applied to Europa, I started exploring the deep atmosphere package in MITgcm with another kind of simple verification experiment using a rectangular geometry. And the small geometry allowed me to really essentially just to run and troubleshoot the simulation on reasonable timescales before we go to a global simulation. So this is just a 3x3x1 kilometer box. So an ocean section that's initially at rest, and then I'm uniformly cooling it from the top. So the goal here was to try and find the smallest scale flow feature that would crop up under this heat flux scenario. So as the fluid layer is cooled from above, you can see that it becomes convectively unstable and overturns. So you can see on the left a vertical section, so that's depth on the y-axis and then x on the x-axis, or width. And then the section on, or part B of this plot is a surface section. So you can see that the scale of the overturning at very early points in the model run was roughly the grid scale, but you can see here at the end of the model run that as the flow matures, the overturning is happening on larger time scales, or sorry, larger spatial scales. And eventually across the ocean domains, you can see kind of overturning, or these, in looking at the figure on the left, these sections of kind of cooler water, the light greens and blues that are extending all the way through this section. So the idea of kind of these sensitivity studies is to essentially to address that third science question, of which is using the code to explore kind of the sensitivity of ocean dynamics on a global scale to a range of variables, like the ice shelf topography or the ocean chemistry, and really understand again how that affects things like overturning and global heat budget. This is still very much in work, but it's kind of it's a fun problem to work on, and I'm very much looking forward to having some global results and tying all these pieces together for Europa. So just to kind of sum it up so far, I think what the work we've done on Earth and understanding kind of the ocean that we know best can really be an important piece of understanding planetary ocean dynamics, where we don't have direct observational data. And I think that ice-ocean boundary layer is a really important region to get right in the model. I think it's the freezing and melting that's happening there is really important to capture well in a global ocean dynamics model. And I think the potential impact of a model like this is it could be used to kind of help assess habitability conditions, inform future space missions, and kind of going back to things that we discussed earlier, maybe trying to understand what's happening underneath that outer icy shell to cause that variety of sort of interesting surface features that we can see. So with that, I will open it up to questions. Thank you for your time.
So our usual policy is either raise your hand or just speak up.
Or for questions, if you want to type your question in the chat, I can read it, or I'll give you a chance to speak up. Yeah, thanks for a super interesting talk, Sarah. So we have a couple of questions in the chat already. Afzal, do you want to ask yours, or?
Yes, I can ask. Thanks. Thanks for the talk, Sarah. It was very interesting. So I was wondering, for this ice-ocean boundary layer, are you or can MITgcm or your code sort of incorporate the eutectic behavior whenever there is salt present? You know, it can depress the freezing point and stuff like that. So I was wondering if that is considered in your model.
Yeah, thank you for that question. That's a really kind of an interesting process that I'd like to capture currently. So as of right now, in the sensitivity studies that I've done, I'm using the standard equation of state for seawater for Earth's ocean. So it does include some of the like turbulent transfer coefficients for heat and salt. And specifically, I think maybe the most important one in this problem is that ratio of the thermal expansion to the Halene contraction coefficients. I have not yet modified that in any way for Europa's ocean. So in part because we don't actually know kind of how salt content or types of salt is different at Europa's ocean. I think in most of the literature, it's thought to be either magnesium sulfate or kind of more standard earth like sodium chloride, so similar. But I'm closely following and hoping that kind of progress is made in understanding how the equation of state for seawater is different at Europa and how I can kind of use that work in my model. But no, currently that's does that answer your question?
Yes, it does. So one quick follow-up. So does your model capture anything related to ice motion, or do you only capture the seawater or ocean dynamics and just put everything else as boundary conditions or source terms?
Yeah, I wish my answer was different. It includes right now just like a static ice shell. So I'm not looking at any intra-ice dynamics. That is a really interesting process, but it again depends on a lot of things that are not well constrained yet. And maybe the biggest of which is that we are still unsure exactly how thick the ice shell is, and kind of the levels and scales of heat fluxes that are occurring there. So right now it's a static ice shell that just includes just at the very interface freezing and melting and phase changes. But it would be very cool in the future to kind of have a more dynamic model of some intra-ice dynamics.
That makes sense. Thank you so much for your talk. Thank you.
Yeah, thank you for the questions.
So another question from the chat, and then we'll go to Natalie, who has her hand raised. So the question is from Eric Hyatt, who says, is the MITgcm capable of employing the enthalpy method?
I don't know the answer to this question. I think maybe there are specific kind of homegrown code packages within the MITgcm community that use the enthalpy method, but not in the packages that I'm using, or kind of the more widely available packages that I've seen so far.
Great. Natalie, do you want to ask your question?
Yeah, sure. I actually have a couple, but I think I'll leave it to just one and follow up with you over email. So I know that Dr. Kang at MIT has been using MITgcm to do some Europa ocean modeling type stuff. And I'm just kind of curious, I guess, like, how do you plan to build on that or deviate from that?
Yeah, it's an interesting question to try and think about, like how to compare this model to, or cross-model validation in general for Europa ocean dynamics, because as I mentioned at the very beginning of the talk, like the boundary conditions and kind of model setups are so enormously different. So kind of to highlight some of the ways that my setup so far is different from Wanying Kang's at MIT's is that I am including phase changes here. So her kind of upper layer of her model is constant heat flux. And so this will kind of be including some of the more like mechanically driven flows from freezing and melting. I think going forward, I'd also like to kind of explore ocean chemistries and the role of double diffusive convection, which is something that her models have not yet done. So I think, yeah, there are a lot of other ways. Introducing topography into the ice shelf is also different kind of from the flat bottom topography that she uses. But yeah, her work is really, really neat and has been really helpful for me to kind of learn how this is done by others.
I have a question as well that sort of relates to something you said at the end there, which is, what was the scale? Can you go back to like when you had your little sketch of the ice shell topography? Like a little cross section kind of right near. Yeah, so I'm gonna force you to go all the way.
No,
yeah.
yeah.
So there's 500 meters of relief on the ice shell at that base of the ice shell there. And I'm just wondering if they're like what the constraints are on the actual relief of the ice shelf for Europe, or the ice shell, I guess, for Europa's ocean, and what processes are creating that relief.
Yeah, so this is something that I'm hoping to explore with this model in the future more, but from kind of my understanding of like the physics and kind of the processes at play here. So small scale topography, much less than this, like really just talking about roughness on the underside of the ice, could be really important in determining kind of the drag coefficient of the ice and the amount of turbulence that you're getting in the boundary layer. So essentially what that would be setting is the skin friction drag of the flow that's just in that region. This is more so getting after modeling something like a larger scale ice feature like a keel or something that could be present in a scene kind of underneath the ice at Antarctica. So what kind of would limit that or contribute to that are things like the pressure environment underneath the ice. So then that would really depend on how thick the ice shell is, which is not yet constrained. So a thicker ice shell theoretically could sustain, I think, like larger features. And this is something that I think Justin Lawrence, he's a former PhD student of Brittany's, very recently he defended kind of in the spring. He's thought a lot about the mechanism, the ice pump, and kind of different circulation mechanisms that could sustain large scale flow features under kind of different temperature and pressure regimes. So it's ongoing research by others, and it's something that I kind of have begun to explore initially, but have really not set bounds on in either direction as far as what's possible.
Yeah. Thanks. So I know there's one question, at least one question in the room, and so I'll open up to the room for questions.
All right, thanks, Tim. So Sarah, great talk. I guess my question is just thinking forward, Europa Clipper and the various data that we think we're going to get from that. What of those data are kind of your highest priority other than the obvious ice shelf thickness one? Are there other elements that would really improve your modeling capabilities here?
Yeah, I think ice shell thickness is the most exciting to me because I think that could be the most useful in kind of constraining a lot of the processes that we could be looking at. But it would also be interesting to see kind of maybe some features that could exist within the ice shell as well. So I think I may have it in a backup slide, so I'll try and get there. But there's been a lot of kind of work and studies that are looking at kind of features that could exist within the ice shell. So melt lenses, kind of brine pockets, things that kind of are a lot more interesting to model and more interesting to think about from a circulation perspective than just like a, thick uniform ice shell. So I think that kind of any information that the radar, the reason instrument could give us about ice shell topography and kind of maybe some non-heterogeneities within the ice shell would be very interesting.
Got it, thanks.
Yeah.
I don't think we have any more in the room here. Shoot.
Okay. Any other questions online?
This is just David. Some of the problems you have related to modeling that very near surface problem, they're very complicated, I understand. Is there something equivalent to, I guess we call it an immersed boundary method, where you apply, like you can create a solid surface by using body forces within a cell. So we do that some in a variety of aerospace and fluid dynamics codes. Is there something equivalent, perhaps where you have like a Lagrangian representation of the interface with points that can move, and then that's separate, like the interface, the solid liquid interface is gridded or triangulated somehow, and then you interpolate those forces and maybe mass fluxes to the adjacent grid cells on your fairly uniform grid? Maybe it's not a well-phrased question. I apologize.
No, yeah, it's really interesting actually. And I've taken some notes while you've been talking about this, because it's not something I've come across personally in the MITgcm kind of literature or the packages that I've explored yet. Kind of on a much larger scale, let's see if I have some pictures. I've kind of explored different types of grid setups within MITgcm and have more recently been going with a cube sphere grid because I think that it makes remeshing a little bit easier at the poles. But that with the level that you've just discussed, I have not explored kind of that amount of detail in how kind of within a certain grid cell, how that can be parameterized. But that's really interesting, and I made some notes. So something
Like, we
future
use
work.
it for doing Navier-Stokes equation, full DNS over like rough surfaces. And we resolve the roughness differently at sort of subgrid levels and interpolate forces to the grid cells. And other people do stuff like that. We've done it with heat transfer as well for compressible flows. And it can possibly be quite simple to implement, or, you know, and not that accurate, or it can be done sometimes much more sophisticated than we ever do it. Anyway, if you'd like to reach out to me and we can chat sometime.
I was just going to say, I'd love to follow up with you on this, on if you have kind of specific sources that you could send my way, or, you know, read up on this. That would be great. Thank you.
Yeah, I can suggest some references to her offline.
Great. All right, well, I think we can wrap up there. This was like a really great, really interesting talk, and a good one to close out the semester on. So thanks, Sarah, for a really engaging presentation.
Thank you for having me. Yeah, and for the awesome questions. I really enjoyed this.
Thank you.
And yeah, we'll reconvene this seminar series in the spring. So everybody have a happy holiday break, and yeah, talk soon.
Take care.
Bye.